10.5a, base e in natural logarithms. In this lesson, we learn a new numerical constant. At some point in your math careers, you learned about pi being the ratio of the circumference over the diameter. Now was big news. Other major mathematical constants are 0, 1, and what we're looking at today is Euler's number E, discovered by Bernoulli when studying compound interest, but turns out it has many more applications than that, including in logarithms. Now, we'll find that if it actually comes up more often in application than the common log with base 10, but because the common log was already taken where you don't write the subscript, we'll need a new notation for a logarithm instead of log to represent the natural log, but it's worth it. You'll see that. Everything else is really the same once you get into the right frame of mind that Euler's number E is really just another number, irrational, like pi, and it's so special that it gets its own number, and mathematicians kept it as lowercase e in honor of Euler. Alright, so it is a constant like pi, and it'll behave similarly, so it follows all the rules, like when you multiply like bases, then you add exponents. Now, you need to know what it approximately equals, and that is e is approximately equal to 2.72. It's irrational like pi, so we know pi is 3.14 approximately, but since it's irrational, it continues without pattern and without ending, just like Euler's number E. It's not pronounced Euler, it's Euler. Okay, so natural logarithms, they have base e, and they have their own notation. So whenever you see this ln, then that's going to represent the natural log, like NL, short for the natural log. You would think that's the notation, but probably eventually the L will look like a 1 at some point. So is that N15 or is that the natural log of 5? To resolve that issue, we're just going to reverse the order, and that's going to give us the natural log of n. You'll see me write it with a cursive L. Now, this is a definition game, so let there be natural logarithms, and then just that's it. They are regular logarithms, log, but with base e. And because they're so special and come up so often, then and that means we don't want to write the base every time because we'll be using these a lot. So to simplify our calculation, then we just do natural log of x. And it's a win-win. Even though the common log base 10 is just log x, that doesn't actually come up the most as we thought it did in the 1600s before Euler's number came around. And we had to switch notations for the natural log then. People are bad at change. So what I'm trying to say, though, is that the natural log here of x would only be 3 characters, and then log x is 4. So I think in the end it all works out. So let's cover some special results. Now, everything from this point forward is the exact same as regular logarithms. Everything. So we're just going to use ln instead. So, and that again means log base e. They are the same. Interchangeable. Looking at the special results. So if you look down here under special results, the natural log of 1 is equal to 0. And here I explain why. So the ln, by definition up here, is really just log base e. And that's a numerical constant, about 2.72. So what do you raise any non-zero number by to get 1? 0. So that's why that is true. So if I say log base 7 of 1, what does that equal? 0, because 7 to the power of 0 is equal to 1. So that's why the natural log of 1 is equal to 0. That's why the common log of 1 is equal to 0. Now, for the next result, this is one where you really want to commit to memory. It comes up a lot, including in this lesson. It makes simplifying exponential equations with logarithmic bases, with bases that have Euler's number E, simplify very quickly. These problems, once you get the hang of it, are even easier than the common log problems. So taking a look here, since ln, the natural log, is really log base e, so I'm just rewriting that. That's how you can conceive of it in your head. Well, you asked the question that all logs represent. What do you raise the subscripted base of e by to get the result of e? Well, that would be just 1, because e to what power is equal to itself. The exponent of 1 will do that for you. So whenever you see the natural log of e, and the e doesn't have an exponent, boom, it equals 1, which usually multiplies out of the problem. So use a calculator if needed to evaluate each expression to 4 decimal places. So you will use the free Graph Calc app for your homework, and it doesn't have Euler's constant in it of 2.72 for e, Euler's number. So what you'll have to do in the calculator is put in 2.72 caret and then negative 8. Hit enter, and your approximate answer, rounding to 4 decimal places, will be about 0.0003355. Other calculators will have Euler's number e already there, just kind of like a pi button. So then in those calculators, you press Euler's number e, it'll bring a caret with a parenthesis, and then you put in the negative 8, close the parenthesis, and you hit enter, and it'll give you the same answer. All right, now the natural log of 1/4. As you remember, the free Graph Calc app on the iPad has a log function. Well, under the function fn FNCS functions or something like that, there is the log function option. Well, we are going to choose the natural log function, which is above the log function. Makes sense because the natural log comes up more than the common log. So what we want to do from here is hit functions, select natural log, and please don't read that as ln, it is pronounced as natural log, and then put in the 1/4, close that, hit enter, and approximately your answer to 4 decimal places is negative 1.3863. And for the natural log of e, right away, boom, equals 1. You can put it into a calculator, especially if it has a button for e, then you could take the natural log of that and get the answer. But remember, ln, the natural log, is shorthand or is equal for log base e. And logarithms are exponents, so what do you raise the base of e by to get e? Just 1. Now that we covered the basics of using the calculator to work with natural logs and Euler's number e when you raise it to different powers, we now want to talk about just going from exponential form with base e to logarithmic form, writing the answer in the end using a natural log, and going from a natural logarithmic equation and writing that in an equivalent version as an exponential equation. So this is just practice with the definition. That's what this is. Now, we've worked with this before, like if we had log base 8 of 16 is equal to 2, that's a true equation, and if I am starting with that and am asked to write that in exponential form, then the 8 is the base, that's the subscript, and then I just swap the 16 and the 2, and there it is, it's true. And you have your 2 forms, your logarithmic and your exponential. We're going to do the same thing here with the base e and the natural logarithm. So e is the base here in this first example, so I go log base e, and then swap the exponent with the result. So log base e of 23 is equal to x. Now I am showing every step, and whenever you have log base e, there is a definition for that. So I am using this first column here when I'm going from exponential to logarithmic. I'm on step 1. I translate it to log base e. Just do like you have always done. But whenever you see a log base e, then you replace it with a natural log, the ln. That's cleaner, and both would work, but it's kind of like having negative exponents. It's not fully simplified. So we replace log base e with a natural log. With the next example, well, we start off with the natural log, and probably right now you don't have it automatic that whenever you see the ln right away you know that's log base e. So it's good until that develops that you replace the natural log, the ln, with log base e. So now we are taking a look at this second column. So we're doing this replacement, step 1. And now this goes back to prior skills, converting from logarithmic to exponential form, where you have this subscripted base here. And then you swap the input of the log with what it equals. So the exponent. And that's also a true statement of equality. And that's an exercise in using the definition of a natural log, which is log base e, and then writing from exponential to logarithmic and logarithmic to exponential. Revisiting the inverse properties. Remember these two? So if you have 5 raised to the log base 5 of, let's say, 3 power, you climb the ladder. When the base matches the base of the log in the exponent, what you were taking the log of in the exponent is your answer. This equals 3. Similarly, if we have, let's say, the log base 6 of 6 squared, that, again, climbing the ladder, when the base of the log matches the base of what you're taking the log of, then its exponent is your answer. So, if that's true with logarithms, log, then it's definitely true with logarithms, natural logarithms, base e. So let's take a look here. This first one, well, the ln represents log base e. Eventually that'll be automatic, and there you have the like bases. Circle, circle, box. But you have to have in mind that the ln, natural log, represents log base e. So just do that translation, rewrite it, and then you'll see everything that you've already learned come into focus. The second one, if I see the ln, I need to simplify, and if I don't see how, I could convert to its equivalent, log base e, and then e to the x, and again we see this ladder, circle, circle, box, and so these two simplify just to x. Let me make one more note here about that second property. So we know the power property of exponents, of logarithms. So if I have the natural log of e raised to the x, that's really log base e of e to the x. And we know with logarithms we can move exponents in front as products. And now what do you raise e by to get e? Well, just 1. So like I said before, whenever you have the natural log of just e with no exponent, that equals 1. And so 1 times x gets x. And so that's why these shortcut properties work. Let's apply them. Evaluate the expression. If it helps you, rewrite the ln natural log as log base e. And now climb the ladder. And 21 is the answer. Next problem. If you don't see it, rewrite the natural log as log base e. Climb the ladder. And x squared minus 1 is the answer. Going into the last section, we will now solve equations and inequalities involving base e, Euler's number. So we will have variables in the exponent attached to the e, so that's why we're going to isolate it first, because it's getting us closer to isolating the variable. Then, because the variable is in the exponent position, we need logarithms. Because it's base e, we will use the natural log. So then we could use this property and quickly get the exponent as the answer. And from there, you really just simplify using this. So let's get underway. In this example, base e with its variable exponent is already isolated. So you could take the common log of both sides. Just a little more writing, take a little bit longer, I think. But now you just need to do the natural log of both sides. The property of equality is what you do to one side, you can do to the other. That's been true for a very long time. So right now, if you're remembering up here this property, we on the left-hand side just get to write 3x equals natural log of 8. If I took the common log of both sides, I'd have a little more work to do than that. In the end, I'll get the same answer, but then I'd have to move this down front using the power property of logarithms. And then I'd have to divide this over to the other side along with the 3. So then I'd get the common log of 8 over 3 common log of e. Now, the common log of e does not simplify to 1. That's log base 10 getting to e. So this, yes, but earning credit doing that? No. What you do is, because it's base e, you recognize that fact by taking the natural log of both sides. Divide by the 3. So that's a 3 down there. Let me make some room over here. And into the calculator, it would look like natural log, parenthesis comes up, close it, hit divide, and then the 3. So x, rounding to 4 decimal places, is equal to 0.6931. For the last two examples, we have to isolate the e first. That's fine. We've done stuff like that before. The reason why is because e has a variable exponent. And we want to ultimately find out what that variable is. It's an unknown, and math is designed to solve for that, to weave through, sift through the complex relationships that define that variable. So I'm going to subtract 4 first. To the other side. Then, to get e with its exponent by itself, I will divide both sides by 3. And now we're back to where we were at the start of the previous example. Because it's base e and we have a variable exponent that we are interested in learning about, we want to introduce the natural log to both sides of the equation. And again, using that inverse property, boom, right away, we get on that side the exponent down and nothing else there. Because, just to quickly remind you, the natural log of e raised to 2v power, I could either use the power property, bring that out front, and then remember that the natural log of e is equal to 1. That's a fact that you need to know. Or you could remember that the natural log is the same as log base e, and there's that inverse property. What do you raise e by to get e? Just 1. So this is all 1. And that's why on the left-hand side we just get negative 2v. Continuing, dividing both sides by v's coefficient of negative 2, get the natural log of 2 all over negative 2. Going for the calculator, substituting that in, rounding to 4 decimal places, v is approximately negative 0.3466. For the last problem with the inequality, as long as we don't multiply or divide by negative, it'll be just like the equations. And so we're starting off by subtracting 10 to the other side. Notice that is a positive 10. So then that means when it goes to the other side, it must change signs. And so we're left with negative 3 e to the y is less than negative 2. Notice that this term's coefficient stays. It did not change signs because it did not change sides. From here, we divide both sides by a negative. So we need to change the direction of the inequality. Now, we still have a variable exponent that we need to solve for. We have base e, so natural log of both sides. And now the left-hand side is just y. Put that into the calculator, rounding to 4 decimal places. Y is greater than negative 0.4055.